Welcome to Ultimate Sleep Doctor. Tonight, we'll explore a quiet wonder, a deep and ancient story unfolding beneath our feet. The Earth itself is in constant, graceful motion, a slow dance of immense plates, shifting and reshaping our world over eons. These enormous sections, called tectonic plates, drift along like silent currents within the planet's warm embrace. It's a process of creation and destruction, of mountains rising and valleys forming, all driven by forces we're only just beginning to truly understand. Consider the vastness of time, the enduring nature of this movement. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe and let your thoughts drift. Let's begin. The Earth, you see, isn't a solid, unyielding ball. It's a truly remarkable place, layered like a giant, incredibly complex cake. We have the crust, the outermost layer, and underneath that is the mantle, a thick, mostly solid layer that's constantly swirling and moving. Deep, deep down, there's the core, a molten sphere of iron and nickel. For centuries, scientists assumed this entire Earth was a single, massive chunk, a frozen, immovable giant. But then, a German meteorologist named Alfred Wegener arrived with a rather startling idea. An idea that would, at first, be met with considerable skepticism. Wegener, in the early 1900s, was fascinated by the shapes of continents. He noticed something quite peculiar. The coastlines of South America and Africa seemed to fit together like puzzle pieces. They weren't just similar, they appeared to be nearly perfect matches, a jigsaw puzzle waiting to be solved. He wasn't the first to observe this apparent fit, of course. Sailors and explorers had noted it for centuries, but Wegener was the first to seriously propose a grand explanation. His initial evidence began with the fossil record. Wegener meticulously collected fossils from across the globe. He discovered that identical plant fossils, specifically fossil ferns and trackways of large reptiles called Glossopteris, were found in South America, Africa, India, and Australia. Glossopteris was a particularly strange plant. It was a widespread, ancient species that thrived in warm, shallow seas. The presence of the same fossil in so many widely scattered continents was a big puzzle. How could a single plant species, adapted to a specific climate, exist on continents now separated by vast oceans? It simply didn't make sense if the continents were fixed in their positions. Furthermore, he discovered glacial deposits, vast stretches of rock smoothed and shaped by ancient glaciers in South America, Africa, India, and Australia. These deposits weren't just small patches. They were massive, extending across entire regions. Glaciers, you see, need very cold conditions to form and survive. The presence of glacial deposits in continents now located near the equator was equally puzzling. It suggested that these continents had once been located much closer to the South Pole, where glaciers could flourish. Wegener reasoned that if these continents were currently in their present positions, there was no logical explanation for these widespread glacial features. He then turned his attention to the geological record. Wegener identified similar rock formations, specifically matching sequences of sedimentary rock, on continents now separated by oceans. These rock formations, composed of sandstones, shales, and conglomerates, displayed strikingly similar characteristics, suggesting they had been formed in the same environments and at the same time. This was further evidence that the continents hadn't always been in their current locations. The patterns of rock layering were incredibly consistent across vast distances, reinforcing the idea of continental movement. Finally, Wegener considered paleoclimatology, the study of ancient climates. He found evidence of ancient shorelines, like coral reefs and delta deposits, in regions that are now far inland. These features indicated that these continents had once been surrounded by warm, shallow seas. Again, this didn't align with their present locations and climate. He compiled all this evidence, the matching fossils, glacial deposits, rock formations, and ancient shorelines, and began to formulate his hypothesis that the continents were once joined together in a single supercontinent he called Pangaea, which, in Greek, means all land. However, despite the compelling nature of his evidence, Wegener's theory faced immense resistance. The prevailing scientific view at the time, largely dominated by British geophysicists, was that the Earth's crust was rigid and immovable. They couldn't conceive of continents drifting across the globe. They argued that Wegener's theory lacked a plausible mechanism to explain how such movement could occur. They questioned the validity of his evidence, particularly his observations of paleoclimatology, suggesting they were misinterpreted or the result of unusual geological processes. Many simply couldn't accept the idea of moving continents. They believed Wegener was a brilliant observer, but his conclusions were fundamentally flawed. There were also concerns about the timing of his evidence. Wegener's dating methods at the time were relatively imprecise, and he couldn't definitively determine when Pangaea had existed or when the continents had begun to separate. The lack of a clear mechanism, a force capable of driving continental movement, was the biggest obstacle. The prevailing view was that the Earth's crust was too strong and inflexible to be moved by any known force. The scientific community largely dismissed Wegener's work, considering it a fascinating but ultimately incorrect speculation. His ideas remained largely ignored for nearly 2 decades. It's a fascinating story, isn't it? A brilliant mind presenting compelling evidence, only to be initially rejected by the scientific community. But sometimes the truth is slow to emerge, and it takes time for the evidence to accumulate and for the scientific community to shift its perspective. The seeds of continental drift had been sown, but it would take further discoveries and advancements in science before Wegener's idea would finally gain widespread acceptance. The mid-ocean ridge systems, those immense underwater mountain ranges, weren't simply geological oddities. They were the heart of a profound and surprisingly dynamic process, seafloor spreading. The initial evidence, as gathered through sonar mapping in the mid-20th century, showed a clear pattern. New oceanic crust was being created at these ridges, and this newly formed crust was steadily moving away from the ridge crests. But how was this incredibly slow, yet continuous, process driven? The answer lay in 2 powerful forces, elegantly demonstrating a restless Earth beneath the waves. The first of these forces is known as ridge push. It's a beautifully simple concept, rooted in gravity. The ridges, being elevated above the surrounding seafloor, create a slope. This slope isn't perfectly smooth. It's riddled with small variations, bumps, and dips. The new, hot, and relatively weak oceanic crust being extruded at the ridge crest is significantly hotter than the crust further away. Because of this temperature difference, the crust at the ridge is less dense and consequently lighter. This creates a constant, gentle downhill movement. It's like pushing on a stack of dominoes. The higher end of the stack exerts a force, and the lower end naturally slides downwards. This downward movement isn't a sudden, violent slide. It's a slow, persistent push. As the hot, new crust moves away from the ridge, it gradually reduces the angle of the slope. The steeper slope is replaced by a less steep one. This, in turn, reduces the force exerted by gravity on the crust. The Earth's gravitational pull continues to act on the entire mass of the oceanic crust, but now that force is directed downward, pushing the crust further away from the ridge. The deeper the crust gets, the more effectively gravity can exert its pull. This downward push isn't a conscious effort by the Earth. It's a consequence of the initial elevation of the ridge and the differing densities of the crust. The magnitude of ridge push is strongly influenced by the rate of seafloor spreading. The faster the crust is moving away from the ridge, the more pronounced the slope becomes, and the greater the push exerted by gravity. Scientists can estimate the rate of spreading by measuring the rate at which new crust is formed at the ridge. This is often done by tracking the movement of magnetic anomalies, variations in the Earth's magnetic field, which are associated with the changing polarity of the Earth's magnetic field and are repeatedly recorded as new crust is created. These anomalies act like markers, showing us how quickly the crust is moving. However, ridge push alone doesn't fully explain the observed rate of seafloor spreading. It's a crucial component of the process, but another, even more potent force was revealed: slab pull. This force, initially hypothesized by Harry Hess in 1962, described a far more dramatic mechanism at work. It's fundamentally linked to the density differences within the Earth's lithosphere, the rigid outer layer composed of the crust and the uppermost part of the mantle. The lithosphere isn't a uniform monolithic block. Instead, it's broken into several large and small plates, constantly moving and interacting. At subduction zones, where one plate slides beneath another, slab pull becomes dominant. Here's how it works. The older, denser oceanic crust that is being subducted is significantly colder and denser than the surrounding mantle. Because of this density contrast, the subducting plate sinks into the mantle with considerable force, pulled down by the Earth's gravity. This sinking isn't a gentle descent. The denser plate encounters increasing resistance from the surrounding mantle material. This resistance creates a frictional drag, effectively pulling the plate downwards. It's like trying to pull a heavy object across a rough surface. The friction provides an opposing force, and you need to apply more and more force to overcome it. The greater the density difference between the subducting plate and the mantle, the stronger the pull. The shape of the subducting plate itself also contributes to slab pull. As the plate descends, it typically bends and folds, creating a concave upward shape. This shape enhances the gravitational force acting on the plate, further amplifying the pull. The deeper the plate sinks, the greater the gravitational force acting upon it. Furthermore, the sinking slab isn't entirely vertical. It often moves at an angle, which further increases the gravitational force exerted upon it. This combined effect, the density difference, the shape of the slab, and the angled descent, creates a powerful, unrelenting force. It's this force that actually drives the movement of the plate, and crucially, it's the primary mechanism responsible for the overall rate of seafloor spreading. In reality, both ridge push and slab pull are constantly operating, albeit with varying degrees of influence depending on the specific location. At mid-ocean ridges, ridge push dominates, driving the initial movement of the crust. But as plates approach subduction zones, slab pull takes over, becoming the dominant force. The interplay between these two forces creates the dynamic and evolving landscape of our planet's oceans, a testament to the incredible power and constant motion within the Earth. The ocean floor, a world of immense pressure and surprisingly complex geology, held a secret. It wasn't a secret whispered by shifting continents, though that was a significant part of the story. This secret was embedded in the very rocks themselves, a record of Earth's ancient magnetic field. Scientists began to realize that the patterns of these magnetic orientations, preserved within the oceanic crust, provided a remarkably precise way to understand how the plates were moving. The key to this discovery lay in a phenomenon called paleomagnetism. The word itself sounds a little complicated, but it simply means ancient magnetism. All rocks, particularly igneous rocks formed from cooled magma, have the ability to remember the direction of the Earth's magnetic field at the time they formed. It's not that the rocks physically hold a magnetic compass. Instead, during their cooling and crystallization, tiny magnetic minerals, mostly magnetite and pyrrhotite, align themselves with the prevailing magnetic field. Think of it like grains of sand on a beach aligning themselves with the wind. Once the rock solidifies, these minerals lock in their orientation, creating a permanent magnetic signature. This process occurs during the solidification of magma. As molten rock cools, the magnetic minerals within the cooling rock adopt a specific orientation relative to the Earth's magnetic field. This alignment is then frozen into the rock structure. Once the rock has solidified, this magnetic signature remains, providing a snapshot of the magnetic field at that particular moment in time. The beauty of this system is that the Earth's magnetic field isn't static. It's generated by the movement of molten iron in the Earth's outer core, a process called the geodynamo. This creates a constantly shifting magnetic field, with north and south magnetic poles that wander over time. The first compelling evidence for this idea came from James Dana in the early 20th century, but it wasn't until the 1960s that the full implications were truly understood. Bruce Van der Merwe and his team were studying the magnetic properties of rocks collected along a mid-ocean ridge, a long underwater mountain chain where new oceanic crust is being formed. They meticulously examined the rocks, analyzing their magnetic orientations. What they found was astonishing. The magnetic stripes running parallel to the ridge system exhibited a clear pattern of alternating magnetic polarity. This meant that in some areas, the magnetic minerals had aligned themselves in a pattern corresponding to a north magnetic pole, while in adjacent areas, they pointed in a direction indicating a south magnetic pole. This wasn't just a random arrangement. The stripes changed their magnetic polarity over time. The researchers noticed that the older the rock, the further back in time it represented. The magnetic stripes weren't actually stripes in the sense of painted bands, but rather sequences of rock formations with distinct magnetic orientations. The crucial insight was that these changing magnetic polarities corresponded to the reversals of Earth's magnetic field. The geodynamo is complex, and the magnetic poles aren't perfectly stable. They frequently flip, switching from north to south and back again, on timescales of hundreds of thousands to millions of years. When the magnetic field reverses, the new magnetic poles establish themselves, and the minerals in newly forming rocks align with the new field. As new oceanic crust forms at the mid-ocean ridge, the minerals within it acquire the Earth's current magnetic orientation. Because the Earth's magnetic field is constantly changing, the magnetic orientation of the newly forming crust also changes. This creates a sequence of rocks with different magnetic polarities, forming a linear record, a stripe, of the magnetic field's orientation. What made this particularly exciting was that the direction of these magnetic stripes consistently pointed in the same direction along the ridge, always moving away from the spreading center, the area where new crust is being created. This meant that the ridge was actively pushing the older crust away from the center, and the magnetic signature was being carried along with it. It was as if the Earth's magnetic field was somehow dragging the ocean floor with it. Scientists realized that they could measure the distance of these magnetic stripes from the ridge axis and use this information to calculate the rate at which the plates were moving. By carefully dating the rocks within each stripe, often through radiometric dating of volcanic rocks, they could determine how long it had taken for a particular magnetic orientation to travel a certain distance. This provided a remarkably accurate way to determine the plate velocity. The measurements were far more precise than previous methods, which relied on seafloor tracking or other indirect observations. The magnetic striping effectively provided a continuous, linear record of plate movement, a magnetic odometer recording the distance traveled by the oceanic crust. The discovery of magnetic striping revolutionized our understanding of plate tectonics. It provided concrete, measurable evidence for the theory of seafloor spreading and the mechanism of plate movement. It demonstrated that the plates weren't simply floating aimlessly. They were actively moving, carrying the oceanic crust along with them. This, in turn, explained the formation of new oceanic crust at mid-ocean ridges and the processes of subduction and continental drift. The study of magnetic striping continues to this day, providing invaluable data for understanding the dynamics of the Earth's lithosphere. It's a testament to the power of observation, careful analysis, and the ability of scientists to unlock the secrets hidden within the very fabric of our planet. The rocks on the ocean floor, quietly recording the history of the magnetic field, have given us a truly remarkable tool for unraveling the mysteries of Earth's restless movement. Deep beneath our feet, a slow, powerful dance is perpetually unfolding. It's a dance that shapes continents, triggers earthquakes, and ultimately governs the very movement of the Earth's crust. This isn't a waltz of continents bumping against each other, although that's a significant part of the story. The real driver of this monumental process is a hidden current, a fiery river of molten rock circulating within the Earth's mantle. This mantle, a thick layer of solid rock extending outwards from the core, isn't as rigid as we might initially believe. It behaves more like a tremendously viscous fluid, extremely thick, but capable of flowing over incredibly long timescales. The mechanism responsible for this flow is thermal convection. Think of a pot of water simmering on a stove. Heat is applied to the bottom, and the water closest to the heat source becomes less dense, rising to the surface. As this hot water reaches the surface, it cools, becomes denser, and sinks back down. This continuous cycle of rising hot fluid and sinking cooler fluid is convection, and it's happening on a scale that's almost incomprehensible. The source of this heat within the mantle is primarily radioactive decay, the breakdown of elements like uranium, thorium, and potassium. These elements are unevenly distributed within the mantle rock, creating warmer pockets. The temperature difference between the hotter, rising plumes and the cooler, descending material generates immense forces. These forces aren't simply vertical. They have a complex three-dimensional structure, influenced by the density variations and the immense pressure exerted by the overlying rock. The mantle isn't one uniform blob of molten rock. It's comprised of many smaller, partially molten regions, some more fluid than others. These regions interact and jostle, creating a tangled network of currents. Now let's consider the scale. The depth of the mantle is approximately 2,900 kilometers, 1,800 miles. That's about twice the radius of the Earth. The flow of material here isn't like the churning of a river. It's a remarkably slow movement, estimated to occur over millions of years. However, even at this slow pace over geological time, the cumulative effect is profound. The rising plumes of hotter mantle material don't simply rise straight up. They are influenced by the surrounding rock and often spread out laterally as they ascend. These rising plumes play a crucial role in plate tectonics. As they push upwards against the rigid base of the overlying lithosphere, the Earth's crust and the uppermost part of the mantle, they exert a force that can initiate the movement of the plates. It's not a direct, forceful push in most cases. Instead, the plume effectively weakens the lithosphere beneath it, making it more susceptible to stress and deformation. This weakened zone can then buckle, fracture, and ultimately lead to the uplift of mountain ranges, like the Himalayas, which were formed by the collision of the Indian and Eurasian plates. Furthermore, the spreading action of these plumes contributes to seafloor spreading. As a rising plume pushes against a mid-ocean ridge, a chain of underwater volcanoes, it creates a zone of weakness. This allows magma to erupt onto the seafloor, building up new oceanic crust and continuously widening the ridge. The heat from this eruption further fuels the convection process, creating a self-sustaining cycle. The density of the mantle material itself is another key factor. As mantle rock cools, a process known as stagnation, due to the lack of movement, it becomes denser. This denser, colder material then sinks deeper within the mantle, completing the convection cycle. This sinking process is particularly important in regions where the mantle is cooling rapidly, such as at subduction zones, where one tectonic plate slides beneath another. The movement of the mantle isn't uniform across the entire planet. There are regional variations in convection patterns, influenced by factors like the geometry of the Earth's mantle and the distribution of heat sources. Scientists use various techniques, including seismic tomography, analyzing the travel times of seismic waves to map these complex convection patterns. These maps reveal that the mantle's flow is far from a simple, global circulation. It's a highly intricate and dynamic system. It's also important to note that the mantle isn't entirely molten. While there are regions of partial melt, the vast majority of the mantle remains solid. The flow occurs through the movement of these more fluid regions, a process sometimes referred to as plastic deformation. This allows the mantle to deform and flow over incredibly long timescales, responding to the stresses imposed by the plates above. The interaction between the convective mantle and the lithospheric plates is a constant, ongoing process. It's a slow, powerful engine driving the dramatic geological events that shape our planet. Understanding this fundamental process, the role of mantle convection, is critical to unraveling the mysteries of plate tectonics and appreciating the dynamic nature of the Earth. It's a story of heat, movement, and time, a story still being written beneath our feet. The Earth isn't a solid, unmoving sphere, not really. It's a restless giant, constantly shifting and changing, sculpted by forces deep within its core. We've explored how the plates that cover its surface, like giant puzzle pieces, are pushed and pulled by the churning mantle below. We've seen the evidence of this movement in the patterns of the ocean floor and the way continents have drifted across time. But there's another, particularly dramatic way these plates interact, a way that produces some of the most intense and visible geological activity on our planet. This interaction is characterized by what are known as transform faults. Transform faults are a type of plate boundary where two plates slide past each other horizontally. It's not a crashing, colliding event like we sometimes hear about, but a slow, grinding movement, a constant, relentless friction. The key to understanding transform faults is to grasp the concept of strain. As plates move, they create stress within the rock. This stress builds up over time, like stretching a rubber band. Eventually, the rock can no longer bear the strain, and it ruptures, releasing the energy in the form of seismic waves, the waves we feel as an earthquake. The location where this rupture occurs is known as the fault zone. The most famous example of a transform fault, and arguably the most studied, is the San Andreas Fault. It runs for hundreds of miles through California, a state known for its frequent earthquakes. To really understand the San Andreas Fault, let's consider its specific arrangement. The Pacific Plate is sliding northwestward, while the North American plate is moving eastward. These plates aren't rushing past each other. They're locked together for immense stretches of time, accumulating enormous stress. The immense pressure causes the rocks along the fault to fracture and renew, creating a zone of intense geological activity. The fault zone itself isn't a single, continuous line. Instead, it's a complex system of smaller faults and fractures, all linked together. These smaller faults accommodate the continuous movement of the plates. Scientists have identified several distinct segments along the San Andreas Fault, each with its own unique characteristics and seismic history. Some segments are relatively stable, experiencing infrequent earthquakes. Others are much more active, producing large, destructive earthquakes with considerable regularity. The behavior of the San Andreas Fault is remarkably consistent. Strike-slip motion. Strike-slip means that the plates slide horizontally past each other, with little or no vertical movement. It's like two hands on a steering wheel turning in opposite directions. The plates aren't jumping or crashing, they're simply moving sideways. This type of movement is far more abrupt and dangerous than one might initially imagine. Because the fault is so long, the stress doesn't dissipate smoothly. Instead, it builds up to a critical point before suddenly releasing, creating the shock wave that produces an earthquake. Scientists use a variety of techniques to monitor the San Andreas Fault. Seismic monitoring stations around the fault record the tiny tremors that constantly occur, providing valuable data about the state of stress and the potential for larger earthquakes. GPS technology is also employed to measure the precise movement of the plates along the fault. By tracking these movements over time, scientists can better understand the fault's behavior and improve our ability to forecast future earthquakes. A challenging, but critically important endeavor. The geometry of the fault also plays a crucial role in determining its seismic activity. The fault is not perfectly straight. It bends and curves, creating areas where the stress concentrates and earthquakes are more likely to occur. These areas, known as slip zones, are carefully studied to understand the mechanics of fault rupture. Furthermore, the surrounding geology, the type of rock, its composition and its structure influences the fault's behavior. For instance, areas with weaker or fractured rock tend to be more prone to earthquakes. The San Andreas Fault is a remarkable laboratory for understanding the fundamental processes that govern plate tectonics. It demonstrates how even seemingly slow, horizontal movement can generate immense forces and create some of the most dramatic geological events on Earth. The complex interaction of the Pacific and North American plates, coupled with the inherent instability of the fault zone, results in a continuous cycle of stress accumulation, rupture, and aftershocks. Studying the San Andreas Fault has not only provided invaluable insights into earthquake mechanisms, but has also helped us develop methods for hazard assessment and mitigation, strategies designed to protect communities from the devastating effects of seismic activity. It's important to note that the San Andreas Fault is just one example of a transformed fault. Similar faults exist around the world, each with its own unique characteristics and seismic history. The Pacific Ring of Fire, a zone of intense volcanic and seismic activity that encircles the Pacific Ocean, is largely defined by the presence of numerous transform faults. These faults are a constant reminder that the Earth's surface is dynamic and ever-changing, shaped by the powerful forces deep within. The movement along these faults is a testament to the enduring power of plate tectonics, a fundamental process that continues to shape our planet today. Deep within the Earth's crust, far beneath the rolling waves of the oceans, a dramatic dance is perpetually unfolding. It's a story of immense power, shaped by heat and pressure, and it's particularly visible at places where two oceanic plates meet. These aren't gentle collisions. They're events of profound geological consequence, oceanic-oceanic convergence. Let's explore this process, focusing on what happens when two vast expanses of seafloor are driven together. The fundamental principle driving this convergence is density. Oceanic crust, the material making up the ocean floor, is relatively young and therefore less dense than the overlying mantle. However, not all oceanic crust is created equal. Some regions of the seafloor are volcanically active, producing crust that is significantly altered, richer in magnesium and iron, and consequently, noticeably lighter in density compared to the surrounding mantle. These lighter, hotter, and partially molten regions are the key to understanding subduction. When two such plates approach each other, the denser plate, often the one with a more mature age and a higher concentration of heavier elements, is inevitably forced downwards. This downward movement isn't a sudden plunge. It's a gradual, complex process that can take millions of years. As the denser plate descends into the mantle, it tears and fractures, creating a deep trench, the most striking feature of an oceanic-oceanic convergent zone. These trenches, like the Mariana Trench, the deepest part of the world's oceans, are physical scars left behind by the immense force of this collision. The trench itself isn't a single, smooth line, but rather a complex zone of deformation, often filled with sediment eroded from the overriding plate. As the subducting plate dives beneath the other, it encounters increasing heat and pressure. This warmth and stress trigger a cascade of events within the plate itself. The rock begins to melt, forming magma. This molten rock, less dense than the surrounding solid material, rises buoyantly towards the surface. However, the overlying plate doesn't simply open up and allow the magma to flow directly onto the seafloor. Instead, the magma is trapped within the overriding plate, accumulating in a magma chamber deep below the surface. The pressure exerted by this accumulating magma profoundly alters the rocks of the overriding plate. Intense heat and fluid flow cause the rocks to become ductile, meaning they soften and flow like incredibly slow-moving, viscous liquids. This process, known as metamorphism, transforms the original basaltic rock into a variety of new rock types, including blue schist, ecleristate, and glaucophane. These rocks, characterized by their vibrant blue or greenish hues, are uniquely formed under the extreme pressure and temperature conditions found in subduction zones. Their presence is a powerful indicator of the zone's depth and the intensity of the subduction process. The rising magma doesn't erupt explosively like a volcano on land. Instead, It tends to build up over time, forming a chain of volcanic islands and arc system parallel to the trench. The Aleutian Islands in Alaska, the Kuril-Kamchatka Arc in Russia, and the Japanese archipelago are all examples of such systems. As the magma ascends and erupts, it cools and solidifies, creating new oceanic crust. This new crust doesn't simply add to the existing seafloor. It actively pushes the older, descending plate further away from the trench. This process, known as overriding, is crucial to understanding how the trench migrates and how the arc system evolves. The geometry of the arc system is closely linked to the angle at which the subducting plate descends into the mantle. A steeper angle leads to a more rapid rate of subduction and a more vigorous arc system, while a shallower angle results in a slower subduction rate and a more subdued arc. The rate of subduction itself is a critical factor, directly influencing the amount of magma generated and, consequently, the intensity of volcanic activity. Furthermore, the process isn't solely about volcanic activity. The immense forces involved also lead to significant deformation of the overriding plate. The plate is repeatedly squeezed, stretched, and folded, creating intricate patterns of faults and folds. These deformations can profoundly affect the seafloor topography, creating complex ridges and valleys. Sediment is scraped off the descending plate and deposited onto the overriding plate, further adding to the complexity of the zone. The entire cycle, the descent of the subducting plate, the generation of magma, the formation of the arc system, and the deformation of the overriding plate, is a continuous, dynamic process. It's a testament to the immense power lurking beneath our feet and a key driver in shaping the geological features of our planet's oceans. Studying these zones provides invaluable insights into the forces that drive plate tectonics and, ultimately, the creation of the continents we know today. The ongoing movement and interaction within these oceanic convergent zones are a constant reminder that the Earth is not a static entity, but a planet in perpetual motion. Far beneath the surface of our planet, a silent, powerful dance continues. It's a dance driven by the immense heat trapped within the Earth, a heat that manifests itself as slow, creeping currents within the mantle. These currents, like rivers of molten rock, are responsible for the movement of the enormous plates that make up the Earth's crust. This constant motion creates a fascinating and sometimes dramatic display of geological activity, one of the most captivating results being the formation of volcanic island arcs. We've seen how oceanic plates can collide, creating subduction zones where material descends into the mantle. Now, let's turn our attention to a very different, yet equally fascinating consequence of this same process: the creation of a chain of islands born from the ocean's depths. The Hawaiian Islands, rising majestically from the vast expanse of the Pacific Ocean, are the perfect example to illustrate this. These islands, comprising a chain stretching nearly 3,000 miles, began their existence not as solid land, but as a single, underwater volcanic mountain. It started around 65 million years ago, during the age of the dinosaurs, when the Pacific Plate began its slow, relentless journey northwestward across the ocean floor. This plate is moving at an average speed of about 10 centimeters per year, roughly the same pace your fingernails grow. As the Pacific Plate drifts, it encounters a hot spot. A hot spot isn't a place on the surface. It's a plume of exceptionally hot magma rising from deep within the mantle, far below the plate. This magma is significantly hotter than the surrounding mantle material, and because of its buoyancy, it pushes upwards, forcing its way through the crust. It's like a persistent, powerful jet of steam trying to break through a barrier. This rising plume sits relatively stationary compared to the movement of the Pacific Plate. The exact mechanism driving these mantle plumes is still a topic of active research, but scientists believe they're linked to larger-scale convection patterns within the mantle. Initially, the hotspot created a single, large volcanic island. However, as the Pacific Plate continued its journey, the area directly above the hotspot remained relatively stable while the plate moved over it. This creates an interesting situation where the same volcanic activity repeatedly occurs at the same location, building up a series of volcanoes. Imagine a train passing over a series of hills. The train keeps going over the same hills repeatedly. With each pass, a new hill is formed. Similarly, the hotspot continues to feed magma to the surface, generating new volcanoes. Because the Pacific Plate is moving, these newly formed volcanoes are continually carried away from the hotspot, creating a linear chain of islands. The oldest islands, located furthest northwest near Hawaii Island, are the most eroded and represent the earliest stages of volcanic development. As you travel southeast along the chain, the islands become progressively younger and less eroded, showcasing the ongoing volcanic activity. Mauna Kea and Mauna Loa on the Big Island of Hawaii, for example, are still actively growing, adding new layers of lava to their summits. The volcanoes themselves are primarily of a specific type, shield volcanoes. These volcanoes are characterized by their broad, gently sloping sides, a result of the fluid basaltic lava flows that erupt from them. Basaltic lava is relatively low in silica, making it runny and allowing it to flow long distances before cooling and solidifying. This contrasts with the more viscous, gas-rich lavas produced at other types of volcanoes, such as stratovolcanoes. The geological processes happening beneath the Hawaiian Islands demonstrate a key element of plate tectonics, the ability of a stationary feature, the hotspot, to produce a linear chain of volcanic landforms as a moving plate traverses its path. It's a beautiful example of the interconnectedness of Earth's systems, the movement of plates, the heat within the mantle, and the resulting formation of spectacular landscapes. Furthermore, the islands themselves are continually evolving. Volcanic eruptions, earthquakes, and erosion constantly reshape the landscape, demonstrating that our planet is a dynamic, ever-changing system. Interestingly, the Hawaiian Islands aren't unique. Many other volcanic island arcs exist around the world, formed in a similar manner at other hotspots. The Aleutian Islands in Alaska, the Galapagos Islands, and the islands of Japan are all examples of volcanic arcs created by the movement of tectonic plates over mantle hotspots. The common thread is the same: a stationary source of heat fueling repeated volcanic activity along a linear trend. Scientists continue to study the Hawaiian Islands and similar volcanic arcs, using techniques such as seismic monitoring, GPS tracking, and analysis of volcanic rocks to understand the processes involved and to refine our models of plate tectonics. These studies provide valuable insights into the fundamental mechanisms that shape our planet's surface and contribute to the ongoing dance of the Earth's plates. So, the next time you think about a faraway island paradise, remember the powerful forces at work beneath the ocean's surface. The slow, steady movement of tectonic plates and the persistent heat of a mantle hotspot, creating a chain of volcanic islands, a testament to the dynamic nature of our planet. The ocean floor, a seemingly endless expanse of blue, isn't quite as empty as it appears. Beneath the waves, a constant, gentle battle is underway, a slow, grinding process of accumulation that eventually sculpts some of the most dramatic mountain ranges on Earth. This isn't a story of sudden, violent upheaval like those associated with subduction zones, but rather a remarkably patient one, involving the relentless gathering of sediment from vast distances. We're going to explore how these accumulations, known as accretionary wedges, build mountains through a process that's both subtle and profoundly powerful. Consider a coastline, any coastline. Waves relentlessly crash against the shore, dragging sand, pebbles, and mud out to sea. This material doesn't just disappear, it's carried along with the currents, sometimes traveling hundreds, even thousands of kilometers. This isn't just local erosion, it's a vast, interconnected system. And this carried sediment isn't uniformly distributed. It tends to cluster around areas of geological weakness, particularly where oceanic crust is being squeezed and deformed by the approaching plate. These weaknesses are often associated with older, flatter regions of the ocean floor, areas that have been repeatedly pushed upwards and downwards by the movement of the plates. These areas become zones of intense deformation. As a plate collides with another, the oceanic crust doesn't simply shatter. Instead, it's intensely folded, faulted, and compressed. This compression forces sediment, initially the same material transported by currents, but now heavily modified, into the gaps and folds created by this deformation. This accumulated sediment doesn't stay neatly stacked. The intense pressures and movements associated with plate convergence cause it to undergo a remarkable transformation. The sediment isn't simply piled up, it's actively rearranged, folded, and faulted, mirroring the deformation of the underlying oceanic crust. Think of it like a giant, three-dimensional puzzle being constantly reshaped. This process is known as accretion, and the resulting structure is called an accretionary wedge. The wedge itself is shaped like a triangle, with the base aligned roughly parallel to the approaching plate. The apex of the wedge, the point where the sediment is most intensely accumulated, is located directly where the two plates are interacting. The intensity of the deformation and sediment accumulation is greatest here, forming the highest peaks of the wedge. As you move away from the apex, the deformation becomes less severe, and the sediment becomes more disorganized, often exhibiting a layered, fisheye appearance due to the repeated folding and faulting. This fisheye appearance is a key diagnostic feature of accretionary wedges. The sediment within these wedges isn't just composed of marine material. As the wedge grows, it incorporates fragments of the colliding plates themselves. These fragments, known as olistolites, are often transported surprisingly long distances before being incorporated into the wedge's structure. They're like geological souvenirs, carried along by the currents of deformation. These olistolites, representing chunks of rock from both plates, provide a fascinating record of the complex movements that have occurred. The growth of an accretionary wedge is a remarkably slow process, measured in millions of years. But over that immense timescale, the repeated accumulation of sediment and the associated deformation create structures that can ultimately rise hundreds, even thousands of meters above the surrounding seafloor. These wedges are not just passively accumulating sediment, they are actively building mountains. The processes happening within an accretionary wedge aren't just about adding material. The intense deformation causes significant changes in the composition and orientation of the rocks. The original layering of the sediment is often completely obliterated, replaced by a complex, imbricated fabric, a pattern of folded and tilted layers. This imbricated fabric is a direct consequence of the shearing and crushing forces that have acted upon the sediment. The study of accretionary wedges provides valuable insights into the dynamics of plate tectonics. They represent a crucial link between the movement of the plates and the formation of mountain belts. Unlike the dramatic, explosive events associated with subduction zones, the formation of accretionary wedges is a more gradual, methodical process. They represent a quieter, but equally important aspect of plate tectonics. Furthermore, these wedges are remarkably common. They've been found along convergent plate boundaries around the world, including along the margins of the Pacific Ocean and the Andes Mountains. The formation of the Franciscan Complex in California, for instance, is a classic example of an accretionary wedge, providing a tangible record of the interaction between the Pacific and North American plates. Analyzing these structures offers scientists a window into the past movements of these plates and the forces that shape the landscapes we see today. The accumulation within an accretionary wedge isn't a static process. It continues even after the initial collision has subsided, as the plates continue to move relative to one another. This ongoing accumulation contributes to the continued growth of the wedge and the surrounding mountain belt. It's a testament to the enduring power of plate tectonics and the remarkable capacity of the Earth to slowly, relentlessly sculpt itself. Ultimately, understanding accretionary wedges helps us appreciate the complex and interconnected nature of the Earth's systems. They represent a powerful demonstration of how seemingly simple processes, the transport of sediment by currents, can, over vast timescales, contribute to the formation of some of the most impressive geological features on our planet. The Earth isn't a solid, unyielding sphere. It's a giant, restless puzzle, constantly shifting and changing shape. While mountains are often built through collisions, there's another, slower, more dramatic way the Earth's crust can dramatically reshape itself, through the creation of enormous valleys, known as rift valleys. These are born not from smashing together, but from a gradual, persistent pulling apart. Let's journey to Africa, to a place where this process is unfolding in spectacular fashion: the East African Rift System. This isn't a single, smooth crack in the ground. It's a vast, complex network of valleys, volcanoes, and lakes stretching for thousands of kilometers, running roughly from Ethiopia through Kenya and Tanzania and into Mozambique. It's one of the oldest and most active continental rift systems on Earth, and scientists believe it's providing a real-time glimpse into the mechanisms of continental breakup, a process that ultimately led to the formation of our continents. At the heart of the system lies the Great Rift Valley itself, a trench-like depression that's nearly 1,000 kilometers long and up to 60 kilometers wide in places. The valley isn't filled with water like a typical river valley. Instead, it's a dry, sparsely vegetated landscape, characterized by steep, jagged cliffs and grabens, down-dropped blocks of crust. A graben is formed when a block of crust sinks downwards relative to the surrounding crust. This happens because the crust is being stretched and thinned. The primary cause of this stretching is the movement of the African tectonic plate. Beneath the crust, huge slabs of rock, called tectonic plates, are constantly shifting. In the East African Rift System, the African plate is slowly, almost imperceptibly, splitting apart. This isn't a simple, clean break. Instead, it's a complicated, multifaceted process involving multiple fault lines and associated stresses. The crust isn't just cracking. It's being pulled apart by the forces generated by the movement of the plates below. This separation is aided by what's known as a mantle plume, a rising column of hot, buoyant material from deep within the Earth's mantle. This plume acts like a giant conveyor belt, pushing the African plate upwards and laterally, contributing to the extension and thinning of the crust. The heat from the plume also weakens the rock, making it more susceptible to fracturing and faulting. The valley floor itself is a mosaic of different geological features. There are volcanic features, like the Nyiramatanga volcanic field in Tanzania, where numerous cinder cones and lava flows demonstrate ongoing volcanic activity associated with the spreading crust. There are also extensive areas of faulted sedimentary rocks, representing ancient marine and terrestrial environments that were submerged and exposed as the crust stretched. These rocks, laid down millions of years ago, now form dramatic cliffs and canyons within the Rift Valley. The lakes within the Rift Valley, including Lake Tanganyika, one of the deepest and oldest lakes in the world, and Lake Malawi, are critical pieces of this puzzle. These lakes are formed in the down-dropped grabens. As the crust stretches, the blocks of crust sink, creating basins that eventually fill with water. The lakes also reflect the ongoing geological processes. Their levels fluctuate dramatically as the crust continues to adjust to the spreading forces. Scientists are studying the East African Rift System because it provides a unique opportunity to observe the early stages of continental breakup, a process that shaped the continents we know today. The system is essentially a laboratory, allowing researchers to examine how continents split apart, how mountains are formed, and how volcanic activity is linked to plate tectonics. The stretching of the crust also generates enormous amounts of heat, which contributes to the melting of rock and the formation of magma. This magma rises to the surface, fueling the volcanoes within the rift system. The volcanoes, in turn, add to the uplift of the region, further contributing to the valley's formation. The rates of extension at the East African rift system are incredibly slow, only a few millimeters per year. However, over millions of years, these tiny movements accumulate, creating colossal changes in the Earth's surface. The valley continues to widen, and the volcanoes continue to erupt, carving out new features and reshaping the landscape. Furthermore, the process isn't confined to just one linear rift. New branches and fault lines are continuously developing, extending the system's reach. Scientists believe that, over millions of years, the East African rift system could eventually lead to the complete separation of the African plate into two or more smaller plates, much like the breakup of the supercontinent Pangaea. The study of the East African rift system isn't just about understanding Africa. It's about understanding the fundamental processes that shape our planet, processes that are constantly at work, albeit often hidden beneath the surface. It's a reminder that the Earth is a dynamic, ever-changing world, and that even seemingly small movements can have profound consequences over vast stretches of time. It offers a compelling look at how continents evolve, how mountains are built, and how volcanic activity is intimately linked to the forces that drive plate tectonics. As the tectonic plates continue their slow, relentless dance, the East African rift system will continue to evolve, providing scientists with invaluable data for decades to come. It is truly one of the most fascinating and active areas of geological research on our planet. The Earth's mantle, that thick, rocky layer beneath the crust, isn't quite as still as it appears. It's a churning, convective system, much like a giant pot of simmering stew. Heat from the Earth's core constantly stirs the mantle material, creating slow, circular movements. These movements are the engine driving the entire process of plate tectonics, and they lead to some of the most fascinating geological features on our planet. But sometimes, this engine generates something a little different, a concentrated area of heat that pushes its way upwards through the crust, creating a volcanic hotspot. These hotspots aren't tied to the movement of tectonic plates themselves. Instead, they sit relatively fixed within the mantle, like a tiny, persistent ember. The formation of a volcanic island chain, as we explored with the Hawaiian Islands, is a fantastic example of this. The Pacific Plate is steadily moving across this stationary hotspot, generating a chain of volcanoes as the magma, rich in silicate gas, rises to the surface. However, hotspots aren't always associated with creating long, linear chains. They can create isolated volcanic features, and that's precisely what happened with the Galapagos Islands. Charles Darwin's voyage aboard the Beagle brought him to these islands, a scattered group of volcanic peaks rising dramatically from the Pacific Ocean. These islands represent the remnants of a hotspot track. The Pacific Plate has moved far away from the original source of the magma, leaving behind the eroded volcanic peaks. The fact that these islands were so far from any continental landmass was a pivotal observation for Darwin, sparking his groundbreaking theories on evolution. Now, let's turn our attention to another remarkable example: Yellowstone National Park in the western United States. Yellowstone sits atop a massive, active hotspot. This hotspot is responsible for the formation of the Snake River Plain, a vast, uplifted region stretching hundreds of miles across Idaho and Wyoming. The initial phase of hotspot activity created a long, linear volcanic field. But as the North American plate drifted over the hotspot, it initiated a more complex pattern. The heat from the hotspot caused the crust to bulge upwards, forming a large, broad caldera, a huge volcanic depression. This caldera, the Yellowstone caldera, is far more than just a collection of steam vents and geysers, though those are certainly spectacular. The heat from the hotspot has permeated the surrounding area, creating a vast system of underground hot springs, fumaroles, and mud pots. The intense heat also keeps the ground perpetually warm, and the mineral-rich waters have sculpted the landscape into a surreal and otherworldly terrain. The caldera itself is about 34 by 45 miles across and contains over 1,000 individual geothermal features. The movement of the North American plate is crucial to understanding Yellowstone's ongoing activity. The plate is moving northwestward at a slow pace, roughly an inch a year. This movement isn't fast enough to completely escape the influence of the hotspot. Instead, the ongoing heat from the hotspot continues to push magma upwards, resulting in repeated episodes of volcanic activity. While large, explosive eruptions like those that formed the caldera millions of years ago are rare today, the potential for smaller hydrothermal explosions and ground deformation remains. Scientists constantly monitor the area, tracking changes in ground elevation, gas emissions, and seismic activity, searching for signs that the hotspot is intensifying. The interplay between the moving plate and the stationary hotspot generates a fascinating feedback loop. The plate's movement creates new volcanic features, while the hotspot continues to provide the heat source. This process isn't static. The rate of plate movement can fluctuate slightly over long periods, and the hotspot's position can shift subtly, leading to changes in the distribution and style of volcanic activity. Interestingly, the Galapagos Islands and Yellowstone aren't the only examples of hotspots driving volcanic activity. There are numerous other hotspots scattered around the globe, each associated with a unique volcanic landscape. The Emperor Seamounts in the Pacific Ocean, for example, are a chain of underwater volcanoes formed by a hotspot track. As the Pacific Plate moves away, these seamounts rise above the ocean's surface, eventually forming islands. Similarly, the Canary Islands off the coast of Africa are shaped by a hotspot. The study of hotspots has profoundly changed our understanding of how volcanoes form and evolve. It demonstrated that volcanic activity doesn't always require the interaction of tectonic plates. Instead, it can be driven by a more fundamental process: the ascent of heat from deep within the Earth. These hotspots highlight the dynamism of the Earth's interior and the remarkable ways in which geological forces shape our planet's surface. Furthermore, the patterns observed in places like the Galapagos and Yellowstone offer valuable insights into the potential for future volcanic eruptions and the risks they pose. Looking ahead, scientists continue to investigate the processes occurring beneath these hotspots, utilizing techniques like seismic surveys, GPS monitoring, and geochemical analysis. These efforts are essential not only for understanding the past and present behavior of these areas, but also for preparing for the possibility of future eruptions and mitigating their potential impact. The study of hotspots is a testament to the ongoing scientific quest to unravel the mysteries of our planet. Ultimately, the story of hotspots and plate movement paints a picture of a truly restless Earth, constantly evolving and reshaping itself through the relentless forces of heat and motion. It's a story of resilience, of creation, and of the profound connection between our planet's interior and its dramatic surface expressions. The sheer scale of the Andes Mountains, snaking along the western coast of South America, has always held a kind of silent, powerful fascination. It's a range that stretches nearly 7,000 kilometers, from the icy tip of Patagonia in Chile to the dense jungles of Venezuela. The question that geologists have tirelessly pondered for centuries is, how did something so immense, so dramatically sculpted, come to be? The story of the Andes is intrinsically linked to the slow, deliberate dance of Earth's tectonic plates, and the evidence for this connection is particularly striking in this region. Initially, the area was part of a large, stable continental platform, a process known as Gondwana, the ancient supercontinent that encompassed nearly all of Earth's present-day landmasses. But over hundreds of millions of years, this stability began to unravel. The most compelling evidence for this unraveling comes from a chain of volcanic arcs, linear sequences of volcanoes that are intimately connected to the Andes. These aren't randomly scattered volcanoes. They form a distinct, almost continuous line, mirroring the shape of the mountain range itself. Consider the volcanoes of Ecuador. The Galapagos Islands, previously discussed as a volcanic hotspot, had an influence here. The plume of magma originating beneath Yellowstone began to leak and spread, creating a volcanic zone along the coast. This wasn't a sudden eruption. It was a gradual, persistent process. The magma, originating deep within the Earth, rose towards the surface, finding pathways through cracks and weaknesses in the crust. As this magma approached the surface, it didn't simply erupt in isolated locations. Instead, it accumulated, forming layers of basalt, dark, fine-grained volcanic rock that represent successive flows. These flows, cooled and solidified, built up over time, creating extensive volcanic fields. But the story doesn't end with the formation of these volcanic fields. The key to understanding the Andes' immense size lies in what happened when these volcanic fields collided. The South American plate, carrying these volcanic arcs, began to move westward, slamming into the much older, denser oceanic plate beneath it, the Nazca Plate. This is where the dramatic uplift of the Andes began. The Nazca Plate, driven by convection currents deep within the Earth's mantle, relentlessly pushed against the South American plate. The process of collision is incredibly powerful. When two tectonic plates collide, the crust buckles and folds, and tremendous forces are exerted upon the rocks. Imagine a very thick carpet being pulled tightly across a floor. The carpet, the South American plate, would wrinkle, fold, and buckle under the pressure. Similarly, the South American plate was subjected to immense compressive forces, causing the rock to deform, fold upwards, and fracture. These fractures created faults, breaks in the Earth's crust where movement has occurred. The geological record in the Andes provides clear evidence of these intense deformations. Geologists have identified numerous folds, faults, and thrust faults where one rock mass slides over another within the Andes. These structures aren't random. They are arranged in a repeating pattern, reflecting the way the South American plate was squeezed and deformed during the collision. The presence of symmetrical folds, where one side of a rock layer is folded upwards and the other downwards, is a particularly strong indicator of compressional forces. Furthermore, the Andes are riddled with a variety of rock types, each telling a part of the story. You'll find thick sequences of volcanic rocks, basalt, andesite, dacite, interbedded with layers of sedimentary rock. These sedimentary rocks, formed from the accumulation of sediments, sand, mud, and organic matter, were deposited in ancient marine environments that existed before the collision. The folding and faulting of these sedimentary layers has created spectacular geological features, like anticlines, upward folds in rock layers, and synclines, downward folds. The deformation isn't uniform across the entire Andes. It's more intense in the western portion of the range, closer to the coast, where the collision with the Nazca plate was most violent. As you move eastward, the deformation gradually decreases, reflecting the fact that the South American plate has been continuing to move eastward, away from the direct influence of the Nazca plate. This eastward movement is still happening today, and it's responsible for ongoing seismic activity, earthquakes, along the Andes. The geology of the Andes also reveals evidence of significant uplift. The range isn't just folded and faulted, it's also incredibly high. The highest peaks, like Aconcagua, are over 6,900 meters above sea level. This uplift is a direct consequence of the collision, as the crust is pushed upwards. Analyzing the orientation of rocks and minerals within the Andes has been crucial. Scientists use a technique called paleomagnetism, studying the alignment of magnetic minerals in rocks to determine the ancient position of the South American plate relative to the Nazca plate. These studies confirm that the South American plate has indeed moved westward for millions of years, providing unequivocal proof of the ongoing tectonic interaction. The story of the Andes is a testament to the immense power of plate tectonics, a process that shapes our planet over vast stretches of time. The dramatic landscape we see today, the towering mountains, the active volcanoes, and the frequent earthquakes, is a direct result of the slow, relentless dance of these two tectonic plates. It's a story written in stone, a geological record etched into the very fabric of the Earth. Let's travel now to a very different part of our planet, the Australian outback. It's a place of vast, ancient landscapes, shimmering deserts and towering mesas, a place where the story of Earth's movement has been etched into the very rocks themselves. Unlike the dramatic mountain ranges of South America or the active rift valleys of Africa, Australia's geological record doesn't scream of violent, recent change. Instead, it whispers a tale of immense, slow processes, of continents drifting across unimaginable distances over billions of years. The key to understanding Australia's movement lies within the outback, specifically in the remarkably preserved, incredibly old rock formations that dominate the landscape. For a very long time, scientists believed that Australia had simply always been there, a stable landmass that hadn't moved significantly since its formation. This view stemmed from the lack of readily apparent volcanic activity or significant seismic shaking. However, detailed study of the outback's geology has consistently demonstrated that Australia has moved, and it has done so in a way that's far more intricate than a simple, steady drift. The most compelling evidence comes from the Proterozoic rocks formed during the Proterozoic Eon, a period stretching from 2.5 billion to 541 million years ago. These rocks are incredibly old, and they hold vital clues to Australia's past. Within the Western Australian Pilbara region, for example, we find some of the oldest exposed rocks on Earth. Some of these rocks are over 3.6 billion years old. These rocks aren't smooth and rounded like rocks sculpted by water or wind. Instead, they're spectacularly folded and faulted, showing evidence of tremendous pressure and deformation. These features aren't the result of a recent earthquake. Instead, scientists believe these folds and fractures formed as Australia was subjected to enormous forces, likely driven by interactions with other plates far to the north. The rocks themselves offer a detailed record of these ancient movements, showing that the Pilbara region, once part of a larger continent, was repeatedly crumpled, stretched, and squeezed as it moved across the Earth's surface. The nature of the deformation is particularly intriguing. The rocks aren't just generally folded. They exhibit characteristics remarkably similar to those found in rocks associated with the breakup of the supercontinent Rhydinia. Rhydinia, which existed around 750 million years ago, was itself a collection of continents, including what would eventually become Australia, clustered together. As Rhydinia began to fragment, the same kind of tectonic processes, folding, faulting, and metamorphism, were active. The rocks of the Pilbara, therefore, represent a snapshot of Australia's involvement in that ancient breakup, suggesting it was once connected to other landmasses that eventually separated. Furthermore, the presence of distinctive rock types, like banded iron formations, layers of sedimentary rock containing alternating bands of iron oxides, is hugely significant. These formations formed in shallow marine environments billions of years ago, and their distribution across Western Australia strongly indicates that the region was once submerged beneath a vast ocean. The shape and orientation of these formations are precisely matched with the predicted movement patterns of Australia, relative to other continents over geological time. The pattern of these formations is similar to what would be expected if Australia had traveled northwards towards the equator, a journey that would have brought it into contact with different oceanic environments and tectonic regimes. Another key piece of evidence comes from the discovery of ancient ophiolites, slices of oceanic crust that have been thrust onto the continents. In the Musgraveshire region of Western Australia, geologists have unearthed remarkably well-preserved ophiolites, which are essentially the remnants of an ancient ocean floor that was squeezed and pushed up against Australia's edge. The age of these ophiolites, combined with the evidence from the Pilbara rocks and the Musgraveshire formations, paints a remarkably detailed picture. Australia was once situated within an ocean basin, and as it moved northwards, it collided with and began to subduct beneath a younger oceanic plate. This process of subduction generated immense heat and pressure, causing the rocks to deform and fold. The evidence isn't solely confined to Western Australia. In the Northern Territory, the Macdonnell Ranges present another compelling story. These rugged, eroded mountains are composed of ancient rocks that have been subjected to similar deformation as those found in the Pilbara. The ranges themselves are a testament to the tremendous forces that shaped Australia's crust, revealing a history of complex tectonic interactions. Examining the rock formations within the Macdonnell Ranges, alongside the data from the Pilbara, offers a more complete understanding of the movement patterns of the Australian continent. Scientists have used sophisticated computer modeling techniques, analyzing the geometry of the rock formations and incorporating data on the movements of other continents to reconstruct Australia's journey across the globe. These models consistently show that Australia has traveled significantly northwards, departing from its position during the early stages of the breakup of Rodinia. The distance it has traveled is substantial, roughly 801,000 kilometers, a journey that occurred over hundreds of millions of years. Importantly, the evidence doesn't suggest a simple, linear movement. Australia's journey has been characterized by periods of relatively rapid movement interspersed with longer periods of relative stability. The complex interplay of plate tectonics, involving collisions, subduction, and rifting, has left a lasting imprint on the Australian crust, creating the unique geological landscape we see today. Studying the Outback's rocks provides a profound understanding of the Earth's dynamic processes and the incredible, patient movement of our planet. It's a story etched in stone, a silent testament to the power and longevity of plate tectonics. The Earth is a restless giant, constantly shifting and changing. We've spent a good portion of this story piecing together the evidence of its movement, examining the dramatic landscapes shaped by mountains rising and falling, and continents drifting across vast oceans. But how do we actually know just how fast these plates are moving? How can we measure something so massive, so deep within the planet with any degree of certainty? The answer, surprisingly, lies in something we use every day: satellites. For decades, scientists have been using a technology called Global Positioning System, or GPS, to precisely track the movement of these enormous plates. GPS isn't just for navigating your phone or guiding delivery trucks. It's a remarkably sensitive instrument designed to determine locations with incredible accuracy. At its core, GPS relies on a network of satellites orbiting the Earth. These satellites transmit signals containing extremely precise timing data. When a GPS receiver, found in your phone, a surveying instrument, or, crucially, a special station designed for plate tectonics, picks up these signals from multiple satellites, it can calculate its own position with a precision of just a few centimeters. Now, let's apply this to the problem of plate motion. Scientists established a network of precisely located receiving stations around the world, often in areas where plate boundaries are clearly visible, like along the coasts of California, Iceland, and Japan. These aren't your typical surveying stations. They're specially designed to withstand the effects of earthquakes and volcanic activity. Each station is equipped with a very accurate clock, atomic clocks, to be precise, that measures time with extraordinary stability. These clocks provide the fundamental basis for the GPS measurements. The key is that the movement of the plate isn't a straight line. Instead, the plates are moving in 3 dimensions, north-south, east-west, and up and down, and at various speeds. By tracking the change in position of these GPS stations over time, scientists can determine both the speed and direction of plate movement. It's like watching a river. You don't just measure how fast the water is flowing horizontally. You also have to account for the current's depth and any swirling eddies. The beauty of using GPS is its ability to capture not just the average movement, but also the short-term fluctuations. Some plates move smoothly and consistently, while others exhibit periods of rapid acceleration or deceleration. These fluctuations are often linked to the stresses and strains building up within the Earth's crust, waiting to be released in the form of earthquakes. By monitoring these changes in real time, scientists can gain a much more nuanced understanding of the dynamic processes occurring beneath our feet. Furthermore, GPS allows for the measurement of vertical movement, which is just as important as horizontal movement. The plates aren't just sliding past each other, they're also rising and sinking. This vertical motion is responsible for the formation of mountain ranges, like the Himalayas, which are formed by the collision of the Indian and Eurasian plates, and also contributes to the subsidence of ocean basins. GPS stations can precisely measure these uplift and subsidence rates, providing a complete picture of the 3-dimensional movement of the plates. The data collected from these GPS stations isn't just used for academic research. It's directly integrated into earthquake forecasting models. By monitoring the subtle changes in ground deformation, the slight stretching or compression of the Earth's surface, scientists can identify areas where stress is building up and where an earthquake is more likely to occur. This information can then be used to issue warnings, giving people precious time to prepare and evacuate. It's a remarkable example of how technology developed for everyday use can be used to protect lives. The accuracy of GPS measurements has steadily improved over time, thanks to advancements in satellite technology and the development of more sophisticated data processing techniques. Newer satellites have higher precision clocks and transmit more frequent signals. Improvements in the software algorithms used to analyze the data have also dramatically increased the accuracy of the measurements. Scientists are now using GPS in conjunction with other techniques, such as INSAR, interferometric synthetic aperture radar, which utilizes radar satellites to map ground deformation with even greater precision and over wider areas. Combining these data sets provides a more comprehensive picture of plate motion and helps to refine our understanding of the complex processes shaping our planet. The ongoing monitoring of plate motion using GPS and related technologies is constantly reshaping our knowledge of the Earth. It's providing us with a real-time window into the planet's hidden dynamics. As we continue to gather data, we'll undoubtedly uncover even more surprises and gain a deeper appreciation for the immense power and complexity of the forces that shape our world. It's a testament to human ingenuity and our persistent desire to understand the natural world around us. And so, the next time you use your phone's GPS to find your way, remember that this technology isn't just about navigation. It's also playing a vital role in unraveling one of the most fundamental mysteries of our planet: the movement of the Earth's massive, ever-shifting tectonic plates. The Earth is a restless place, a slow dancer constantly shifting and reshaping itself over immense timescales. We've already begun to unravel some of its secrets through looking at the movement of continents and the patterns in rock formations. But there's another, incredibly subtle, key that scientists use to understand what really happened millions of years ago. A clue hidden within the very magnetic properties of rocks. This is the story of paleomagnetism, a field that allows us to rewind the Earth's history by examining the magnetic orientations locked within ancient rocks. The fundamental principle behind paleomagnetism begins with a simple, powerful phenomenon: magnetism. Just like a compass needle, a magnet has a north-seeking pole and a south-seeking pole. But the Earth itself is a giant magnet. This magnetic field, generated deep within the Earth's core, a swirling mix of molten iron, extends out into space, protecting us from harmful solar radiation and influencing the behavior of compass needles. Now, here's where it gets really interesting. As molten iron swirls within the outer core, it generates electric currents, and electric currents, in turn, create magnetic fields. This is a continuous, self-sustaining process. As rocks form, particularly volcanic rocks, they often contain magnetic minerals like magnetite and pyrrhotite. These minerals have a remarkable ability. They can remember the direction of the Earth's magnetic field at the precise moment they solidified. When molten rock cools and forms, the magnetic minerals align themselves with the surrounding magnetic field. It's like a tiny, natural compass, recording the orientation of Earth's magnetic field at the time of their creation. This alignment isn't permanent. The minerals can slowly reorient themselves over incredibly long periods due to processes like heat and stress. However, for a significant time, the initial alignment remains remarkably stable, often for millions of years. The crucial observation came in the early 20th century, spearheaded by physicists like Samuel Young. Young noticed something peculiar: rocks from different locations, Even rocks of the same volcanic eruption consistently pointed in slightly different directions when plotted on a map. Rocks from one area might point north, another a little to the east, and yet another to the west. Initially, this was a complete mystery. It seemed like a fundamental error in the way scientists were measuring the Earth's magnetic field. However, the repeating pattern quickly led to a revolutionary conclusion. The Earth's magnetic poles weren't fixed in a single spot. Instead, they had moved and were continuing to move over geological time. The realization that the magnetic poles were wandering was a watershed moment. But it wasn't just about knowing that the poles moved. The repeating patterns of different orientations from rocks in different locations provided a powerful tool for reconstructing the past positions of the magnetic poles. Scientists began to collect rock samples from all over the world, carefully documenting their magnetic orientations. They quickly discovered that the patterns weren't random. They displayed a distinctive, repeating, jigsaw puzzle-like structure. This pattern is known as apparent polar wander. It's called apparent because it's not the actual movement of the magnetic poles themselves, but rather the apparent movement of the poles as seen from the surface of the Earth, considering the movement of the continents. Think of it like this. If you were standing on a spinning top, you'd perceive the North Pole to be moving around you, even though the North Pole itself isn't actually moving. Similarly, the continents have moved relative to the fixed magnetic poles, and this has created the illusion of polar wander. The key to understanding this apparent polar wander lies in the concept of seafloor spreading. As new oceanic crust is formed at mid-ocean ridges, it carries with it rocks that have recorded the magnetic field orientation at the time of their formation. As the seafloor spreads outwards, these rocks create a continuous record of the magnetic field's direction, much like a giant magnetic tape. The repeating pattern of these magnetic stripes, bands of alternating magnetic polarity, provides a highly accurate timeline of seafloor spreading and, consequently, the movement of continents. The data from paleomagnetism has been instrumental in refining our understanding of plate tectonics. By carefully analyzing the magnetic patterns preserved in rocks from various continents, scientists have been able to calculate the distances and directions that continents have moved over millions of years. This information has been used to create incredibly detailed reconstructions of past plate configurations, allowing us to understand how the continents were once joined together in supercontinents like Pangaea, and how they have gradually drifted apart. Furthermore, paleomagnetic data has helped us resolve significant discrepancies in the evidence for plate movement. For instance, the evidence from rocks in Australia was initially challenging to reconcile with the overall picture of plate tectonics. However, analysis of the magnetic orientations revealed that Australia had rotated relative to the established plate boundaries, a phenomenon called continental rotation. This rotation explained why Australian rocks appeared to be oriented differently than expected, given the perceived movement of the surrounding plates. The story of paleomagnetism is a testament to the power of observation and the remarkable ability of rocks to remember the past. It's a crucial tool in unraveling the intricate history of our planet, revealing the slow, relentless movements that have shaped the continents and oceans we see today. It's a constant reminder that the Earth is not a static object, but a dynamic, evolving system, and that the clues to understanding its past are often hidden within its most unassuming features. The continuing study of paleomagnetism promises to reveal even more secrets about our planet's past, further refining our understanding of the grand dance of plate tectonics. The Earth is a restless place, a slow-motion dance of colossal forces. Beneath our feet, the ground isn't truly solid. It's a jigsaw puzzle of enormous shifting plates. These plates, like giant rafts floating on a viscous layer of the semi-molten mantle, are constantly interacting, colliding, separating, and sliding past each other. This movement, driven by heat from deep within the Earth, is responsible for nearly all the dramatic geological features we see across our planet. Let's travel to a particularly spectacular example of this process, the Himalayas. For millions of years, a vast area of the Earth's crust, largely submerged beneath the Indian Ocean, was quietly accumulating sediment, sand, silt, and decaying plant matter, forming a relatively flat, stable platform. This platform, known as the Tethys Sea, was a thriving marine environment, teeming with life and rich in resources. It was a landscape steadily building upwards, a stage for the evolution of countless species. The plates were moving, but slowly, almost imperceptibly, with India steadily drifting northward across the Earth's surface. Around 50 to 70 million years ago, during the early part of the Cenozoic era, the Indian plate began a dramatic acceleration. It wasn't suddenly slamming into anything, but its movement increased significantly, driven by a complex interplay of forces within the mantle. This increase in speed is what ultimately made the collision with Asia so catastrophic and so transformative. The Earth's mantle is not uniform. It has zones of hotter, less dense material rising and cooler, denser material sinking. These convection currents, acting like a giant conveyor belt, are a key driver of plate movement. As India continued its northward journey, it encountered the edge of the Eurasian plate, a vast, ancient crustal plate that stretched across Europe and Asia. The Eurasian plate wasn't simply standing still. It too was undergoing subtle movements. The interaction between these two plates wasn't a head-on smash, but rather a complex process of oblique convergence, meaning the plates were moving at an angle relative to each other. This is crucial to understanding how the Himalayas formed. Imagine pushing a toy car diagonally into a wall. The force isn't concentrated in one direction, but spreads out, causing a greater impact at an angle. The immense force exerted by the collision caused the crust to buckle, fold, and fracture. The Indian plate, being denser and younger, was forced underneath the lighter, older Eurasian plate in a process known as subduction. Subduction is where one plate slides beneath another, and it's a primary mechanism for mountain building. As the Indian plate plunged beneath the Eurasian plate, it didn't simply sink smoothly. The friction and immense pressure generated during this process caused the crust to be intensely deformed. This deformation resulted in the uplift of the entire region. The crust thickened dramatically, and the folded and faulted rock layers were pushed upwards, creating the towering peaks of the Himalayas. Think of squeezing a sponge. The material is compressed, and it rises. The Himalayas are a gigantic, ongoing consequence of this squeezing action. The mountain range is still growing today, as the Indian plate continues to push northward, adding centimeters per year to its height. The Himalayas are not a single, uniform mountain range. They are a complex system of peaks, valleys, and ridges, shaped by countless factors including erosion, weathering, and ongoing seismic activity. The high altitudes and rapid uplift have created extreme conditions, intense cold, strong winds, and significant variations in elevation. Glaciers carve deep valleys into the mountainsides, while rivers rush down from the peaks, transporting vast amounts of sediment. The collision has also been responsible for some of the most powerful earthquakes on Earth. The immense stresses built up along the boundary between the plates are periodically released in the form of seismic waves. The Himalayas are located along the Ring of Fire, a zone of intense volcanic and seismic activity surrounding the Pacific Ocean, and the Indian plate's collision with Eurasia is a major contributor to this activity. Scientists meticulously study the fault lines and seismic patterns in this region to better understand and predict these potentially devastating events. The Himalayas represent one of the most dramatic examples of plate tectonics in action. It's a testament to the immense power lurking beneath our feet, a reminder that the Earth is a dynamic and ever-changing planet. The jagged peaks, the deep valleys, and the powerful forces that shape this incredible range will continue to evolve for millions of years to come. The journey of the Indian plate and its collision with Eurasia has sculpted one of the most magnificent landscapes on Earth. The Earth's crust isn't one solid, unbroken shell. It's like a giant jigsaw puzzle made up of enormous pieces called tectonic plates. These plates are constantly moving, driven by forces deep within the planet. While we've spent considerable time observing their movements along continents and witnessing the majestic rise of mountain ranges, a significant, often hidden, consequence of this movement plays out in the deepest parts of our oceans, the formation and evolution of deep-sea trenches. These aren't merely underwater valleys. They represent some of the most dramatic and intense geological processes happening on Earth. These trenches, the deepest parts of the world's oceans, aren't formed by simple erosion, like a river carving a canyon. Instead, they are the product of a powerful and specific interaction between tectonic plates. Most deep-sea trenches are found at subduction zones. A subduction zone is precisely where one tectonic plate slides beneath another. It's a dramatic, slow-motion collision, and it's this collision that sculpts these immense underwater canyons. The process begins with the convergence of two plates, typically an oceanic plate and a continental plate, or sometimes two oceanic plates themselves. The denser plate, often the older, colder, and therefore denser oceanic plate, is the one that is forced to descend. This descent isn't a gentle slide. It's a powerful, often violently abrupt process. The angle at which the plate descends is crucial, influencing the trench's geometry and the conditions within. Shallow angles create relatively short, steep-sided trenches, while steeper angles result in longer, more gradually sloping features. As the plate plunges into the mantle, it doesn't simply disappear. Instead, it heats up dramatically due to friction with the surrounding rock and the immense pressure. This heat causes the rock to partially melt, creating magma. This magma doesn't always erupt onto the surface as volcanoes. Those often form further away, where the descending plate weakens the crust. However, the magma generated within the descending plate still exerts considerable influence. It can create bends and irregularities in the trench itself, and it plays a key role in the geological activity occurring along its length. The weight of the descending plate also exerts tremendous pressure on the surrounding mantle. This pressure can cause the mantle material to deform and flow, creating complex geological structures. These movements aren't always smooth. They're characterized by fracturing and faulting breaks in the rock where movement has occurred. These faults, often running parallel to the trench, contribute significantly to the trench's overall shape and stability. The deeper you go within a trench, the higher the pressure becomes, impacting the rock's physical properties and influencing the processes occurring within. The Mariana Trench, located in the western Pacific Ocean, is the deepest known trench on Earth, reaching a staggering depth of nearly 11,000 meters. It's formed by the subduction of the Pacific Plate beneath the smaller Philippine Sea Plate. The extreme pressures and temperatures within the Mariana Trench are unlike anything found on Earth's surface. Scientists have developed specialized submersibles to explore this extreme environment, revealing a world of bizarre creatures adapted to these harsh conditions. These organisms thrive on chemical energy derived from the interactions between the seawater and the rock, showcasing remarkable examples of adaptation. Beyond the Mariana Trench, similar subduction zones are responsible for the formation of trenches across the globe: the Peru-Chile Trench, the Tonga Trench, the Kermadec Trench, and many others. Each trench possesses a unique history, reflecting the specific plate interactions that created it. Studying these trenches isn't just about understanding the formation of deep-sea features. It provides valuable insights into the processes that shape the entire Earth. The sediment accumulation within trenches is also a fascinating area of study. Because trenches are often areas of high water flow and geological instability, they act as traps for sediment eroded from the surrounding areas. This sediment, consisting of everything from fine clay to large boulders, accumulates over millions of years, creating thick layers that can reach hundreds, even thousands of meters in depth. These deep-sea sediments offer a valuable record of past climate conditions, sea levels, and geological events. Scientists analyze the composition of these sediments to reconstruct the history of the region. Furthermore, trenches are areas of intense seismic activity. The stresses built up within the subducting plate, coupled with the movement of the overriding plate, can trigger powerful earthquakes. These earthquakes, often occurring at depths within the trench itself, are among the largest and most destructive on Earth. The study of seismic activity within trenches helps scientists understand the mechanics of plate tectonics and improve earthquake forecasting capabilities. The ongoing process of subduction doesn't just create trenches. It also plays a critical role in the cycling of elements within the Earth system. As the descending plate returns to the mantle, it carries with it water and other volatile compounds. These compounds then contribute to the melting of the mantle, influencing the formation of new oceanic crust and impacting the composition of the entire planet. This continuous exchange of materials highlights the interconnectedness of Earth's geological systems. Finally, research into deep-sea trench environments continues to push the boundaries of our understanding of Earth's processes and the remarkable life forms that can survive in some of the most extreme conditions on the planet. The Earth's surface isn't one solid, unbroken shell. It's a vast, intricate puzzle, constantly shifting and reforming. This restless movement, the driving force behind plate tectonics, isn't just about mountains or trenches. It's intrinsically linked to where we find volcanoes, those fiery expressions of the planet's inner heat. Volcanic activity isn't random. It's a direct consequence of the way the Earth's plates interact. The heat that fuels volcanism originates deep within the Earth, a residual warmth from the planet's formation and the ongoing decay of radioactive elements within its mantle. This heat doesn't simply ooze upwards. It's trapped and pressurized, accumulating in a zone roughly 100 to 700 kilometers below the surface. This immense heat creates areas of weakness, zones where the mantle rock becomes pliable and capable of slowly moving. The movement of these mantle plumes, gigantic columns of hot, buoyant material, is the primary source of magma, molten rock that will eventually erupt onto the surface as a volcano. However, the location of these eruptions isn't determined solely by the presence of the plumes themselves. It's the interaction between these plumes and the movement of the tectonic plates that dictates where we see volcanic activity. There are three main ways plate boundaries influence volcanism. The first is at divergent plate boundaries, where plates are moving apart. Think of it like squeezing a tube of toothpaste. As the edges separate, the molten rock from the underlying mantle rises to fill the void. This happens most dramatically at mid-ocean ridges, underwater mountain ranges where new oceanic crust is constantly being created. The magma, being less dense than the surrounding rock, rises and erupts, forming new oceanic crust and basaltic volcanoes. Iceland, sitting directly atop the mid-Atlantic ridge, is a stunning example. A country built entirely from volcanic eruptions fueled by the divergence of the North American and Eurasian plates. The second major influence is at convergent plate boundaries. Here, plates collide. The outcome of this collision depends on the types of plates involved, whether one is an oceanic plate and the other is a continental plate, or two continental plates. When an oceanic plate collides with a continental plate, the denser oceanic plate subducts or plunges beneath the lighter continental plate. As the oceanic plate descends into the mantle, it heats up and releases water. This water lowers the melting point of the surrounding mantle rock, causing it to melt and generating magma. This magma then rises to the surface, forming a volcanic arc, a chain of volcanoes parallel to the trench that forms at the plate boundary. The Andes Mountains in South America, formed by the subduction of the Nazca Plate beneath the South American plate, are a classic example of this process. The Cascade Range in North America, with volcanoes like Mount St. Helens, is another, showcasing the same fundamental mechanism. The process at convergent boundaries isn't always straightforward. The angle at which the oceanic plate subducts significantly impacts the style and intensity of the volcanism. Shallow subduction angles produce more explosive eruptions, as the water released at depth quickly flashes to steam, dramatically increasing the pressure within the magma. Steeper subduction angles tend to result in quieter, more effusive eruptions. Furthermore, the age of the oceanic plate being subducted plays a crucial role. Older, colder oceanic crust is denser and more likely to subduct smoothly, while younger, warmer crust tends to fracture and create a more complex, volatile subduction zone. The third major setting for volcanism is at intraplate volcanic regions. These are areas of volcanism that occur far from plate boundaries. The most famous example is the Hawaiian Islands. These islands aren't located at a plate boundary. Instead, they are formed by a hot spot, a plume of unusually hot mantle material that is stationary relative to the moving tectonic plates. As the Pacific plate slowly drifts over this stationary hot spot, the plume produces a chain of volcanoes, with the youngest volcanoes forming directly above the hot spot and the older, eroded volcanoes forming a chain behind them. Another example is Yellowstone National Park in the United States. Like Hawaii, it's also situated over a hot spot. Beneath the park lies a massive magma chamber, and although eruptions are less frequent than in other volcanic regions, the potential for large-scale eruptions remains. The movement of the North American plate over this hot spot causes the landscape to uplift and subside, creating the characteristic geysers and hot springs. The distribution of volcanoes globally isn't a coincidence. It's a direct reflection of the dynamic processes occurring within the Earth's mantle, interacting in complex ways with the movement of the tectonic plates. Studying these patterns, the location, frequency, and style of volcanic eruptions, provides invaluable insights into the Earth's internal workings, allowing scientists to better understand the forces shaping our planet and, importantly, to anticipate and mitigate the hazards associated with these powerful, fiery displays. It's a constant conversation between heat, motion, and rock. The Earth isn't a solid, unmoving sphere. It's a restless giant, a constantly shifting puzzle built of enormous, slow-moving pieces. For a very long time, scientists puzzled over why earthquakes happened, why mountains rose, and why volcanoes clustered in certain locations. They observed that these events weren't random. They seemed connected, happening in patterns. It took a brilliant mind to put all these observations together and create a revolutionary idea, the theory of plate tectonics. This theory suggests that the Earth's outer shell, the lithosphere, is broken into several large and small plates. These plates aren't floating on magma, but rather, they are part of the lithosphere and are being carried along by the movement of the hotter, more fluid mantle beneath. It's like a cracked eggshell. The shell itself doesn't move, but the contents underneath, the magma, flows and pushes the shell around. The driving force behind this movement isn't fully understood, but scientists believe it's related to heat escaping from the Earth's core, creating convection currents in the mantle. These currents act like a giant conveyor belt, slowly dragging the plates along. The most dramatic evidence for this theory comes from the study of seafloor spreading. Along mid-ocean ridges, enormous underwater mountain ranges rise from the depths of the ocean. At these ridges, new oceanic crust is constantly being created as magma rises from the mantle and cools, forming solid rock. As new crust forms, it pushes the older crust away from the ridge, much like continental plates are doing today. Scientists have meticulously mapped these spreading ridges and measured the rate at which the plates are separating, sometimes several centimeters per year. This speed is surprisingly fast, yet over millions of years, it creates tremendous distances. But the theory of plate tectonics goes beyond just seafloor spreading. It also explains the distribution of continents. Over vast stretches of geological time, these continents have repeatedly collided and separated, forming and breaking apart supercontinents, massive landmasses that once encompassed almost the entire planet. The most famous of these supercontinents is Pangaea. Around 335 million years ago, during the late Paleozoic and early Mesozoic eras, the continents were joined together in a single, enormous landmass, Pangaea. It was a truly awe-inspiring sight, a single continent stretching from pole to pole. North America, South America, Africa, Antarctica, and Asia were all connected, separated only by shallow seas. This wasn't a static arrangement, though. The forces acting on Pangaea were immense, resulting in significant geological activity across its entire surface. The collision of Pangaea's constituent plates was responsible for the formation of the Appalachian Mountains in eastern North America, which were uplifted and eroded over millions of years. Simultaneously, in the western part of the supercontinent, the forces were creating the Rocky Mountains, a much more recent mountain range formed by the collision of the North American plate with the Eurasian plate. The vast inland seas, such as the Panthalassic Ocean, surrounded Pangaea, shaping the landscapes and influencing climates across the globe. The sheer size of Pangaea meant that the effects of plate movement were amplified. Volcanic activity was widespread, and the movement of massive crustal blocks caused significant uplift and subsidence. The climate itself was dramatically different than what we experience today. Because Pangaea was so large, it had a smaller surface area relative to the amount of solar radiation it received. This led to a colder climate overall, although there were still significant regional variations. Around 200 million years ago, as the continents drifted apart, Pangaea began to break apart. The rifting process started in the center of the supercontinent, creating a massive basin that would eventually become the Atlantic Ocean. The breakup wasn't instantaneous. It was a gradual process that took tens of millions of years. As the continents separated, the original mountain ranges of Pangaea began to erode, and new mountain ranges were formed along the boundaries of the newly separated plates. The fragments of Pangaea continued to drift apart, gradually forming the continents we recognize today: North America, South America, Africa, Europe, and Asia. The geological features we see today, the mountains, the trenches, the volcanoes, are all remnants of this ancient supercontinent and the powerful forces that shaped it. The cycle of supercontinent formation and breakup continues, driven by the relentless movement of the Earth's plates. Scientists continue to study the evidence left behind by Pangaea, analyzing rock formations, fossils, and geological structures to understand the processes that drove its formation and breakup. The story of Pangaea is a testament to the dynamic nature of our planet and the immense timescale over which geological processes operate. It's a reminder that the Earth is not a static entity, but a living, breathing world in constant motion, shaping the landscapes and influencing the climate for millennia to come. And while Pangaea is long gone, its legacy remains etched in the Earth's surface, a silent witness to the planet's incredible history. The Earth's crust isn't a solid, unbroken shell. Instead, it's broken up into enormous puzzle pieces, the tectonic plates, that are constantly, though very slowly, moving. This movement isn't a smooth, gliding motion. It's a complicated dance involving immense forces deep within the planet. And at the heart of that dance, where the plates meet, lies the origin of some of the most dramatic events on Earth: earthquakes. These are not random acts of destruction, but rather the inevitable consequence of the plate boundaries doing what they do best: interacting. When plates collide, or pull apart, or slide past each other, the rock beneath the surface responds in a remarkable way. This response begins with a sudden fracturing of the rock. This fracturing isn't a clean break like slicing a loaf of bread. Instead, it's a complex process called fault rupture. A fault is simply a fracture or zone of fractures in the Earth's crust where the rocks have moved relative to one another. There are several types of faults, but for our discussion, we'll focus on strike-slip faults, where plates slide horizontally past each other, and dip-slip faults, where they move vertically. During fault rupture, the rock doesn't break all at once. It's more like a giant, tangled rope being pulled apart. Initially, small cracks form, and these cracks rapidly spread, branching out like the roots of a tree. This spreading creates a zone of weakness within the rock, a zone where stress is concentrated. The energy built up over decades, centuries, or even millennia is suddenly released. This release of energy is what we experience as an earthquake. The exact shape and size of the ruptured zone depend on the type of fault, the orientation of the rocks, and the amount of stress present. Scientists use techniques like seismic reflection surveys, essentially bouncing sound waves off the Earth's subsurface, to map these ruptured zones in detail, helping them understand the mechanics of the earthquake. Now, let's consider what actually happens during the earthquake. The sudden movement of the rocks generates powerful vibrations that travel through the Earth. These vibrations are what we detect as seismic waves. There are two primary types of seismic waves: P waves, or primary waves, and S waves, or secondary waves. P waves are compressional waves, meaning they travel by squeezing and expanding the rock in the direction they are traveling. Think of pushing and pulling a spring. They are the fastest seismic waves and can travel through solids, liquids, and gases. S waves, on the other hand, are shear waves, meaning they move the rock perpendicular to their direction of travel, like shaking a rope up and down. Critically, S waves cannot travel through liquids, which is a key factor in determining the composition of the Earth's interior. The initial rupture of the fault creates a complex pattern of seismic waves. The first waves to arrive at a seismograph, the instrument used to detect earthquakes, are typically P waves, followed by S waves. The time difference between the arrival of these two waves and the distance to the earthquake's epicenter, the point on the Earth's surface directly above the focus, or the point of rupture underground, can be used to calculate the distance to the earthquake's location with remarkable accuracy. This is how seismologists around the world pinpoint the origin of an earthquake. Once the initial rupture has propagated along the fault, the released energy continues to radiate outward in the form of aftershocks. These are smaller earthquakes that occur in the vicinity of the main shock, the initial, large earthquake. The aftershocks often cluster around the main fault rupture, but they can also occur along related faults. The intensity and frequency of aftershocks can last for days, weeks, or even months, depending on the size of the main shock and the geological conditions. Studying aftershocks is just as important as studying the main shock itself, as they provide valuable information about the fault's geometry, stress distribution, and overall behavior. Furthermore, the waves generated by an earthquake don't just travel outwards in straight lines. They are refracted and reflected by changes in the Earth's density, the variations in rock type, temperature, and pressure, causing them to bend and bounce. This complex wave propagation creates a three-dimensional image of the Earth's subsurface, allowing scientists to understand the structure and properties of the rocks along the path of the seismic waves. The study of seismic waves and fault rupture provides a powerful tool for understanding the forces driving plate tectonics and predicting the potential for future earthquakes. By analyzing the patterns of seismic wave arrival times and the distribution of aftershocks, scientists can identify areas of high seismic hazard and develop strategies for mitigating the risks associated with these powerful natural events. It's a continual process of observation, analysis, and understanding, slowly revealing the intricate dance of the Earth's plates. The Earth, our swirling, dynamic home, hasn't simply been sitting still for billions of years. It's been gently, relentlessly moving. This movement, this profound and ongoing shift of continents, is driven by the very forces we've come to know as plate tectonics, and understanding where we're headed, how fast and in what direction, is a fascinating, though complex, scientific pursuit. The pace of this movement isn't constant. It fluctuates, sometimes slowing down dramatically, other times accelerating with surprising force. These changes, though subtle over human timescales, have shaped landscapes, influenced climates, and ultimately will continue to define the future of our planet. Scientists use a variety of techniques to measure this movement, primarily relying on very precise tracking of GPS satellites. These satellites, orbiting high above the Earth, can detect incredibly small changes in position. By comparing the satellite's positions to known benchmarks on the ground, often permanent monitoring stations, scientists can calculate the rate at which the tectonic plates are drifting. The results, compiled over decades, paint a picture of movement that's not uniform across the globe. The Atlantic Ocean, for example, is widening at a rate of roughly 2.5 centimeters per year, about 10 inches. That's about the same speed that a redwood tree grows, though thankfully, the continents aren't growing alongside them. However, the rate isn't a simple, consistent number. The Pacific Plate, a massive ring of oceanic crust surrounding the Pacific Ocean basin, is actually moving eastward at a significantly higher rate, approximately 10 centimeters per year. This is driven by the subduction of older, denser oceanic crust beneath younger, more buoyant material, a process that feeds the immense volcanic activity we've discussed. The interactions within the Pacific are particularly complex, involving the convergence of multiple plates and the resulting deformation of the crust. Looking further into the future, predicting the exact movement of the continents isn't like predicting the weather. It's not about forecasting a specific event. It's about building models and understanding the underlying forces that govern plate motion. The most influential forces are the mantle convection currents, massive currents of heat within the Earth's semi-molten layer beneath the crust. Think of it like a giant conveyor belt, with hot, less dense material rising and cooler, denser material sinking. These currents exert drag on the plates, driving their movement. The Earth's magnetic field itself plays a subtle, yet important, role. As the Earth spins, it generates a magnetic field that shields us from harmful solar radiation. This magnetic field is produced by the movement of molten iron within the outer core. This movement influences the flow of material in the mantle, further affecting plate motion. It's a complex, interconnected system, and accurately modeling it is a monumental challenge. Scientists use sophisticated computer simulation to test different scenarios. These models incorporate data on plate velocities, magnetic field strength, and variations in mantle density. The simulations allow them to explore potential future configurations of the continents. One particularly significant prediction centers around the long-term fate of the Atlantic Ocean. Over hundreds of millions of years, the Americas are predicted to continue moving away from Europe and Africa, eventually drifting completely across the Atlantic. This process, known as the Wilson cycle, suggests that continents repeatedly assemble, break apart, and reassemble, mirroring cycles that have played out throughout Earth's history. It's crucial to understand that these predictions are based on the long-term behavior of the Earth system. They aren't concerned with the immediate impacts of earthquakes or volcanic eruptions, though those events are certainly influenced by plate tectonics. Instead, they are concerned with the fundamental processes that will shape the planet over vast timescales, millions or even hundreds of millions of years. The rate of continental drift is also intimately tied to the cooling of the Earth's mantle. As the mantle cools, it becomes denser, which increases the drag on the moving plates. This means that over very long periods, the overall rate of plate motion is likely to increase. Furthermore, the geometry of the plates themselves will change. The continents will continue to fragment and reform, potentially leading to entirely different arrangements of land masses compared to what we see today. While predicting the exact details of the distant future remains beyond our capabilities, the underlying principles are becoming increasingly clear. The Earth's tectonic plates are not static. They are constantly moving, driven by forces deep within our planet. Understanding these movements and the processes that govern them offers a profound appreciation for the dynamic nature of our world and allows us to better anticipate the long-term impacts of plate tectonics on the very shape of our planet. The Earth will continue its journey, a slow, powerful dance that is shaped and will continue to shape the landscapes and climates of the future. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. We've journeyed beneath the Earth's surface, understanding the slow dance of our planet's plates. Let your thoughts drift now, calm and unhurried as the mysteries of the deep settle around you.